right, as soon as Chrome gets done crashing, come on, you got this. So right now, it looked like there were 3 people waiting. I don't know. Chrome's in the process of crashing right now. It'll be back with us in just a minute. But I should still be able to see your comments in the chat. So it looks like there's 3 of you waiting. 4 of you waiting. So what questions do you have for me today? I didn't receive any emails, so the only updates, I made a mistake last live stream. It's actually Orgo 2, your exams is next week. Orgo 1, your exams are this week. Can we go over number 20 through 32 in the homework and can review page 25 through 29 in the study packets? So let me bring up the homework. So we'll alternate. Madeline, go ahead and ask your question while I look up Elijah's. '20 and 32 is like, oh, that's a long range. We can do them, but okay. So we'll start with question 20. So question 20 asks that we have the molecular formula C4H8Cl2, and we want to do one where there's chlorine at the end. And CLs, we want CH3s at each chain. The question is asking, you've got the structure formula C4H8Cl2, which of these carbons belong, in which none of these belong to methylene groups. The methylene group is going to be your CH2. So CH4, it tells you it's linear off the bat. And what we don't want is any CH2 groups. So we've got Cl's at the end, and then we've got CH3s. Now, the formula for a saturated hydrocarbon is C4, for C4 will be C4H10, but 2 of our hydrogens are being replaced by hydrogens, so this is a saturate. We don't get any double bonds in this case. So if we've got Cl's at the end, and we don't want a methylene, I've had to solve this before. I know for the CH3 one, this one's pretty easy. So for the CH3, we end up with the CH3s. We don't want any CH2 groups. We just put a Cl and a Cl. How do we do C4H10 without any Cl's at the end? Or we want the Cl's at the end. Well, we have one option is we can draw a linear, which makes it impossible because we got a Cl. But another option is that, let's see here. All right. So if I make it 2-methyl propyl, and if I put one Cl here, I've got a CH2 group. So if I put a Cl here, I end up having a CH. So this is a methyne, this is a methyne, this is a methyl, and this is methyl, but I don't end up with the methylene groups. So let's see if that works. So we want the chlorines at the terminal end. So I got my two structures. I have the one dichloro 2-methyl propane, and then I have 2-chloro 2-methyl butane. Let's see if this works. Oh, oops. Wrong problem. I meant to put those here. Okay, so that's the answer to 20, is that you have the dichloro and then you have the ones that were on the... Oh, anyway. So Madeline's asked for question 21, so let's go to the next one. What is the hybridization in each carbon atom in this molecule here, and what are the bond angles? I'm not a huge fan of quizzing on the bond angles. I asked this question mostly for the hybridization. I'm not a huge fan of bond angles because there's the ideal bond angle, but the reality changes a lot depending on what's bound around the atom. So we've got 1, 2, 3, 4, 5 atoms. Now, in terms of hybridization, for carbon, we've got 4 possibilities. sp3, three possibilities, S and sp. You're going to have an sp3 when you have a tetrahedral carbon. In this case, it's going to be carbon with 4 bonds. Or I shouldn't say 4 bonds, 4 periphery atoms. So if it's got 4 atoms around it, then it's sp3. If it's got 3, it's sp2. And if it's only got 2, then it's sp. So for this one, if I draw in the hydrogens, H, 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 H. This carbon has 2 atoms around it, 1, 2, so that makes this one sp. This one's also sp. This carbon has a carbon here and here. This carbon has 1, 2, 3, so it makes it sp2. This one is sp2, and this one is sp3. Now, in terms of bond angles, for sp3, this is 109 degrees. For sp2, it's definitely 120 degrees. And then for sp, it's 180 degrees. But again, I'm not a huge fan of testing on that type of material. So let's see if it accepts my hybridization. Now for A, B, C, okay, I see where it's asking for the bond angles. For atom A, B, and C, since that's an sp2 hybridized carbon, that's going to be 120 degrees. Same thing for B, C, D. And then C, D, E, if we have an sp hybridized carbon, it's 180 degrees. You're welcome. All right, question 32. Click the draw structure button and draw the formula with tert-butyl 3-methylheptane. So to draw any type of structure, start reading it right to left. We have heptane, 1, 2, 3, 4, 5. And we get to arbitrarily pick the starting position. I like left to be the start. 1, 2, 3, 4, 5. So now we just read it off. So we have 4 tert-butyl. So there's going to be Wow, they intentionally did this to mess with you. This is not numbered correctly. So we have 3-methyl. So there's a methyl group hanging off the third carbon. And for the fourth one, tert-butyl is actually a shorthand for 2,2-dimethyl ethyl. The way I remember tert-butyl, it's a T shape. So that's actually, tertiary refers to third, so this is a tertiary carbon attached to it. But for me, the T is the easiest to remember. So let me draw the structure in here. It's also weird because that's not the correct IUPAC name for this either. And we'll talk about that when you see the structure. Wait, hex, hep, there's 7. Sorry, pentane's 5, heptane is 7. But even then, I don't agree with that's the longest chain here. So let me flip it around so you can see it. So this is structure I've drawn. Let's see. Yep, thinks it's correct. Now, why is it I don't think this is the correct IUPAC name. 2, 3, 4, 5, 6. I guess it is. Heptane would be 7. It's just a very complicated chain. 1, 2, 3, 4, 5, 6. Yeah, it is a heptane. Yeah, tert-butyl is a shorthand. It's still used quite a bit, so tert-butyl alcohol is the T with an OH on it. It does show up. You need to learn it. It's like isopropyl. Isopropyl is the Y. So anytime you see a 3-train, it's 1-methyl ethyl. But yeah, the propyls do show up. Sec-butyl is the other weird one. So secondary butyl means that you're attached to the secondary carbon of a 4-member ring. So this is sec-butyl. And this is isopropyl. I understand why we use this shorthand. It's a lot easier than saying, particularly with this one, methylpropyl or methyl ethyl or dimethyl ethyl. But on the other hand, it's also not IUPAC naming. The whole point of IUPAC is that you have prefixes. You're not memorizing what are effectively trade names. All right, page 25 through 29 of the study packet. Ah, the synthesis problems. Good. So pages 25 through 29, if we were doing the acetic course, this would actually be what the back end of your exam would look like. So this is more akin to what the free response should be, as well as some of the multiple choice questions. So the thing about actual organic chemistry, and you're going to find this out when we start doing the synthesis in Orgo 1, you can ask the Orgo 2 students, it's great to say, I'm going to put these things together and make this. The reality is you're going to make a whole bunch of other stuff in the process, and you need to verify that you made what you actually made. So for all the types of problems that follow on those what you see on the back ends of all these packets, these are synthesis combined with analysis. So this is going to take the test 1 material and apply it to what you're learning for test 2. So the first question on page 25 asks that you have the reaction of cyclohexane with chlorine. And you run this reaction. The thing about chlorination is that it's not actually a very selective reaction. We end up getting mono-substitute, which is what we prefer, di and tri-substitute. And it gives you a list of possibilities of what could have been made. So for whatever reason, when this reaction was run, we were able to separate it out. And these were three possibilities that were considered. So the question is, based on the data, what did we actually end up producing? And for when you see mass spec, mass spec is asking you about the molecular weight. So if we look at cyclohexane, it's, let's see here, it's 72 plus 12, so it's 84 AMUs roughly. So the question is, what do each of these weigh? So chlorine weighs 35.5. We lose a hydrogen and we gain a chlorine. So for every chlorine that gets attached, we add 34.5 AMUs. So this one's going to weigh 118.5. This one's going to weigh 153, and the last one's going to weigh 187.5 AMUs. So if we look at the mass spectra, and I'll bring it up on my end. The heaviest peak in the mass spec is sitting a little under 120. Why do I feel like I did this wrong? 672. It's probably not the dichlorinated, it's probably the monochlorinated. I'll correct the key in that regard. I think it's supposed to be the monochlorinated species. But this is the one, yeah, definitely monochlorinated. So this is the one that's actually produced when we run the mass spec, because it weighs the 118.5. So we see a peak at 118 and a peak at 119 and everything that we'd expect for making monochlorinated compounds. The next one, you're given a reaction of bromine, you're asked, okay, which one did you actually make? So again, halogenation not being that particularly sensitive, and even then we're just kind of seeing output from a separation process. So there's a possibility here that we're just seeing products come off of a separation, and we want to know which particular product we've isolated. And so we have one attachment here, one attachment here, and one attachment here. So you're given a simulated NMR spectrum, and your NMR spectrum has a quartet, a septet, a singlet, a doublet, and a triplet. Now, to figure out which one we've made, in practice what we're going to do with NMR, it's really hard to back derive things from NMR, like figure out a structure based on the NMR. It's actually a lot easier to kind of have a model and go off the model. And the big one with this I would look for is the singlet. So if we look at the packets, it says there is a singlet at a chemical shift of around 1.2. Well, the thing about singlets is that in order to get a singlet, we have to have a molecule where we have hydrogen atoms on a carbon group that are isolated from their peers. So there's only two structures here where we end up with a methyl group that's actually isolated from the rest of the molecules. This one, these two methyl groups are isolated, and this one, these methyl groups are isolated. This compound here, we never have hydrogens that could produce a singlet because every single one has a carbon with a hydrogen that has a vicinal hydrogen on it. So these would not produce a singlet because of that one, and vice versa. This wouldn't produce a singlet because of this one, and vice versa. This wouldn't produce a singlet because of this, vice versa. So automatically we know the last one's out. Now we look at the rest of the peaks. We've got a septet, a singlet, a triplet, a doublet. Now the singlet here has an area of 3, which means it's only 3 hydrogens that are isolated. So if I look at the area, this is the only one that will produce a singlet with an area of 3 relative to the rest. These two are going to have an area of 6. Now I also need to go through, I need to verify that this statement's actually true. So can I find a quartet, can I find a septet, can I find a singlet, or can I find a triplet and a doublet? So in terms of doublets, I have 2 here because these see 1 hydrogen, and this one would see 6 hydrogens, so I would have my septet here. So I see my septet, I see my doublets, and Here I would have a triplet, and here I would have a quartet. So everything else about this molecule is consistent with the NMR tables. This one wouldn't produce it. One, there's the wrong area. Two, these would not form simple splitting patterns. This would be a triplet of quartet of triplets or triplet quartets. This one would be a doublet of quartets or a quartet of doublets. So that's pretty much how the rest of these work out. You're going to go through and you're going to look at what it's proposing and say, okay, based on what you're seeing in the table, does this make sense? Like the next one is carbon 13 NMR, and the way I would approach this type of problem would be to look at it and say, okay, well, I need a molecule where I've got basically 5 carbons where there's 2 pairs that look like mirror images of each other. So there's only one that looks like this. This one has carbon here, these 2 are mirror images, and the methyl groups are mirror images. That isn't true for the rest of these. So probably what I produce here is the 2,2-dibromo species. And what's the last one? 1H NMR still follow. Ooh, that's a nightmare pattern. But yeah, it's going to follow that approach. Yeah, that's pretty much how you do the whole back end, is look at your molecules that you're given and ask yourself if they're consistent with the spectrum beneath, and try to look for unique identifying features, like particularly with 1H NMR singlets. If you can find isolated methyl groups, those are the easiest to see in the molecule. If you see them, that tells you that could correspond to the NMR spectrum. Particularly if you don't see them, you can eliminate as a possibility and you don't have to worry about working like the rest of the table. So 252 question. The discussion board this week was an industrial process. There are so many wonderful things about that process that would be dangerous. Let's look it up. I would agree halogenation is pretty dangerous. So I'll show Orgo 1 students what the discussion board was this week. So for Orgo 2, you're given this process. You have, let's see, that's 2,5. You have 1-pentanol being reacted with PCC, and then the product of cyclopentane with bromine followed by magnesium. Those react. That gets reacted with PDC, and then it gets reacted with the product of chlorination and eventually the lithination. We'll call it lithination of that product. So I'm inclined to agree with you. I think the halogenation is probably the most dangerous part. With the Grignards themselves running a very close second, you could argue either one being more dangerous. The issue with Grignards is they can be pyrophoric. There's actually, when I was in grad school, there was a grad student at the University of Los Angeles that died working with a Grignard reagent because it set her on fire. So yeah, either of those would be a really good candidate for being particularly nasty regarding the safety of this reaction. Halogenation I would worry about personally, just because with halogenation, it's not just that it's bad for the environment, it creates horribly corrosive chemicals that will eat through the reactor. So over time, you're looking at a really good possibility of your reactor failing just due to degradation. But that said, if you're doing high volume output with this process and you've got like gallons and gallons of Grignard sitting in the reactor, if that spills out, you're going to have a gigantic fire on your hand that you're not really going to be able to put out. You're welcome, Elijah. Acid catalyzed reactions are probably not that big a deal. The truth is, if you have an acid spill, just pour a whole bunch of baking soda on it and you're done. Third place would be that PDC, PCC, anything, because that's pyridinium dichloride, like pyridium chromium chloride, I think was the other acronym, PCC. Both of those contain halogens. They're not necessarily dangerous in the sense that the halogens are there. It's the chromium that's in it that's super toxic. You have a lot of choices with the discussion board about what's super dangerous about that reaction. Pentaprefix, yes. So 35 was 1, 2, 3, 4, 5, 6, 7. So it was 3-methyl isobutyl. I looked at it. It looked like it should go through that butyl group. It doesn't. So if we start here, 1, 2, 3, 4. If we do this, it's 5, 6. If we do this, it's 5, 6. And if we do this, it's 5, 6, 7. So it is heptane. 7 carbons is the longest chain in that molecule. Any other route would give you 6. So it just is, it is correct. It is a heptane. It's just got a really complicated branch onto the side. By IUPAC naming, so you have a methyl, and then you have 2,2-dimethyl propyl heptane. If you were to do it like this, then I would say that you would end up with, did I remember that one correctly? Oh yeah, so it would be 3-methyl 4 2,2-dimethyl propyl heptane, or you can do the tert butyl, but the butyl is going to come first because B comes before the M. Oh, that really big one, CH. Okay, so the penta in that case, question 35. So the version it's giving me 235. The reason where the penta comes from in your example is that if we count up the number of carbons, there are 35 carbons. In this case, there are 37 carbons. And so with this one, it's going to be, this is just the weird Latin, your penta and then your number for 30. So I'm thinking it's triacon. For my example, it would be hepta, tri-con-tane. But that penta there is to designate the 1 position, and for mine, since there's 37 carbons, the 7 would designate the hepta. Yeah, and I can show you on my end. So I don't know enough Latin to know why that is why it is, but the hepta and the penta in your case is just coming because of the 1's position and the number of carbons. But it's got to be something about how you number things in Latin. That would be my guess. Definitely not German. 48 in the online homework. So identify the structure below that represents the most stable conformation of trans 1,2-isopropyl 3-methyl cyclohexane. So 1-isopropyl. Three-methyl cyclohexane. So I'll show you my version of the problem. So which ones can I eliminate off the bat? Well, they're 1 and 3, which means they have to be 3 atoms apart. So for the first one that works, for the second one that works, for the third one that works, for the fourth one, this is 1, 2. So I can eliminate. I keep a tally on the board behind me. Actually, tell you what, let me just draw them for you on the board behind me. Not doing any favor with these drawings. Okay, so the first one, we're just going to automatically discount, and the reason we can automatically discount is that it doesn't say, oh no, this is your time. Ask as many questions as you need. First one we can discount because your line bond drawing doesn't tell you anything about the stability, or this projection here doesn't tell you anything about the stability because it's not designating axial or equatorial. So that's gone. This one they're 1, 3. This one they're 1, 3. This one they're not 1, 3. This is 1, 2. So we can automatically eliminate this one. This one is 1, 2, 3, 4. So we can eliminate the third possibility, that possibility. And the same thing's true of the last one because this is 1, 2, 3, 4. So this leads us down to these two possibilities. Now, this one we can eliminate because it's tert-butyl. So there's really only one possibility here that works without having to know anything about the stability. Now, that said, if it wasn't so nice and didn't give you obviously wrong answers, what we would look for is one that, since it is trans, we would need to determine if it's possible to have them both axial and both equatorial. So if I draw this correctly, and 1, 2, 3. So if this is axial, then if I had a cis, it would be equatorial, and the cis here would be axial, so it would be equatorial. So since this is the trans version, it would tell us that one has to be axial and one has to be equatorial. And whichever one puts the bulkier group in the equatorial position, that's going to be the more stable one. But for that one, you can eliminate all of them simply because most of them aren't even drawn correctly to make that work. Now, maybe it's different if there's like a 1,4 variant of this problem. You're going to have to do a little bit more work. But even for the 1,4 variant, the tert-butyl ones disappear. That one disappears. The 1, 2 disappears. Yeah. It looks like the trick to this problem was just like eliminating everything that wasn't even correctly drawn. Right. What's your next question, Madeline? $50. Can you review the specific difference between stereoisomers and conformational isomers? All right, so let's pop over. Oh, actually, I'm on question 50 right now. So a stereoisomer are ones that are related by you're changing RNS, so you're changing the chirality. A conformational isomer is one where you're just changing it by a carbon-carbon single bond rotation. And then a constitutional isomer is one where they're just connected in a different order. So for stereoisomers and conformational isomers, if I write the formulas out, I don't do the line bond drawing, I can't tell the difference between the two. For conformational isomers, they're going to look different in space. So basically, where's my kit? If I have or if I have heptane in this case, just turning this molecule around and rearranging it, all of these are different conformational isomers. But if I were to throw a chiral center into it, so we're just stick an oxygen on here. For the stereoisomers, the only way, the other stereoisomer is the one where I have the oxygen on the other side. Now, it's still connected to, in this case, the third carbon, but there's no way I can rotate this to get it back to the other version where the oxygen's on the other side. And with constitutional isomers, I would literally have to just take the whole molecule apart, break bonds, and reconnect it. So for the example it gives me on my end, it asks, are these stereoisomers, constitutional isomers, or different conformations of the same molecule? So if I look at it, I've got 1, 2, 3, 4, 5, 6, 7 atoms, six carbon atoms connected in a chain. All I've done is rotate between the second and third atom and kind of twirl the molecule around. So I would say different conformations. For stereoisomers, you would need to see like wedges and dashes, or you would have to see actual chiral centers. There's no chiral centers in this molecule. And for constitutional, they wouldn't be connected all in the same way. Ooh, the next question, 51, is pretty good about that too. So this is a good example of a stereoisomer. So if we look at question 51, at least my version of it, asks, you have cis 1,2-dimethyl-cyclopentane and trans 1,3-dimethyl-cyclopentane. So they're both cyclopentanes, but the methyl groups are connected to different things. We have 1,2 and 1,3. We actually have to make and break bonds to do this. So they're definitely not conformational isomers. But since the atoms aren't connected in the same place, they have a different formula. This would be a constitutional isomer. Now, if I were to take the same molecule and say, okay, cis 1,2-dimethylcyclopentane versus trans 1,2-dimethylcyclopentane, the trans in that case, those would be stereoisomers. So when you have the RS or the cis trans or the EZ, and that's the only difference between the molecules, those are stereoisomers. 56. The following question relates to cyclohexane ring depicted in the chair conformation. Is a methyl group at C6 that is up or down, axial or equatorial? So the way we designate axial equatorial that's barely visible on your end. So in this projection, axial and equatorial, axial is up and down, equatorial is left and right. So if I go to the problem, if a C6 group that is down, that would be axial. Oh, I thought there might actually be more to that problem. But yeah, we do up-down to designate axial, and we do left-right to designate equatorial, and that's just because that's what they are. Axial is along a z-axis. Equatorial is perpendicular to that axis. So 1, 2, 3, 4, 5, 6. Those are all axial. Then 1, 2, 3, 4, 5. Those are all equatorial. You're welcome, Nicole. Do you have an example of which questions were used up and down and the results were equatorial? Because that'd be something I need to report to the publisher. Let's look at the next one. The following molecule sexting ring depicted in the chair conformation is a methyl group that is up at 1 more or less stable than a methyl group that is up at C4. I would say it has the same stability. What? That makes no sense. A C4 is down and an up methyl group would be equatorial. Okay. That's why their question makes no sense. Way to go, McGraw-Hill. I was really curious. A little curious how that was confusing. Okay. So if we have an up group at the first carbon position versus an up group at the fourth carbon position, these alternate. So in the 2D projection, not in the 2D projection, in the line bond drawing, easiest way to visualize it drawing it? For me, the easiest way to visualize it is to build the molecule. Um, but some people can do the drawings in their head, I think, particularly if they've done it long enough. So when they say up, down, they're not referring to this drawing, they're referring to the line bond drawing, and that's really not clear in that problem. So if the first carbon is axial, if it's the next one's cis, it would be equatorial, axial, equatorial. Because they alternate when we take the molecules, when we take the cyclohexane and we bring it down. So let me build it and show it. So this molecule is this molecule here on your left. Oh, I agree. That is horribly misleading because we don't describe it as up down. We describe it as wedge dash. So if we pop the first one up and we bring it into the chair conformation, these were all cis to begin with. Make sure you can actually see it. So the first one was cis. Make that one red. All these started out cis to the first carbon. So the second one would be axial, third one would be axial, second one would be equatorial, third would be axial, fourth would be equatorial. So in the drawing, to get the other group, methyl group equatorial, we would draw it quote unquote up in this drawing. Although no one would ever call it that, they would call it a wedge draw. We would give it a wedge bond. That explains a lot. Okay, no, the problem is just very poorly worded. It's not you. Why would you call it that? Because that's also the next question. Which is more stable, up or down? Again, it's actually talking about the two-dimensional. It's talking about the actual three-dimensional projection. It's asking if the first carbon was a wedge bond, would it make more sense to draw it as a dash bond to make it more stable? Oh, that's just a poorly worded question. Other questions in the remaining 7 minutes? Excuse me. Part 2 of question 59. Oh, great. That was when I was actually working. So this one you're going to go back and it's asking if you were to convert that drawing to a line bond drawing, would they be wedged or dashed? So yeah, it's the same idea. In my case, we ended up having this drawing. Again, it's going to alternate. So let's say this one's equatorial. Well, if it was cis to this one, it would be axial, equatorial, axial. So if they were both cis, one would be axial, one would be equatorial. So then to make them both equatorial, it would have to be a wedge. So they would be trans to one another. At least in the version I have. All right, with the last minute left, again, if you're on Orgo 1, your exam is, how did we use the entire time already? Yeah, that's, your exam is due Sunday at midnight. Keep in mind, Monday and Tuesday are fall breaks, so those of you in the Tuesday lab, don't show up. I mean, you can, but I'm not going to be there. There's also no live stream Monday. I'm kind of around by email this weekend, but definitely not so consistent. If you do see an issue with the exam, shoot me an email. If it's a really unfair question, I'll give you back the points for it. Next week, Orgo 2, y'all will have your exam opening up, and then the following Friday, your homework will be due for the second exam. So, good luck on your exams, and I will see some of you next Thursday.